Good day again. Evan Snyman for Umukluko, looking at our second installment in the financial mathematics topic. Today we're going to be looking at the FV, or what is called the future value formula. Okay, so last lesson we saw that logarithms, a topic that we did elsewhere in mathematics, came into play with financial maths, which is kind of unusual. And today we're going to see that another topic of maths, namely from geometric sequences or geometric progressions and series, come into play. So if you think about it, okay, in the old days, we used to do a barter system. So if I borrowed 5 Rand from you, I would give you 5 Rand back, okay? And that was how it used to be way back when. Straightforward borrow and lend idea. Then we grew to an idea of simple interest. And with simple interest, we saw that what would happen is you would pay back more and more money the longer you held on to it, okay? But it was a linear relationship, and depending on where we started at let's say this was the p-value over here, let's say that was the p-value over there. In the case of the old barter system, no matter how long you borrowed the money, okay, you would owe, so this would be time, the scale on the horizontal scale would be time, okay? No matter how long you borrowed the money, you would owe them the same amount no matter what, okay? Using the simple interest, this is a linear relationship, and so it would go up according to your interest rate, okay? And so this was simple interest, and the gradient of the slope would be your I value, okay? So your slope here would be your I value. Okay, we then moved on to the idea of compound interest. And please understand, all these things were happening as people's technology and their access to more and more sophisticated calculating devices. So in this case, it would have been some early calculators or some early computers came along. And so this thing grew under exponential growth. Okay, so this was compound interest. Okay, and it was an exponential growth. Okay, so it was exponential. And many people will say to you, nothing grows faster than exponential growth. Okay, now I want to look at one more thing quickly here, and unfortunately I'm running out of colors, but what then happened was we got computers, the early days of computers, which allowed us to say, cool, instead of paying you only at the end of the year, I could calculate the interest at the end of the month, or at the end of the quarter, or at the end of the, in modern times, actually at the end daily or hourly. So that became I over IM to the power of n times m. And this one would have grown just ever so slightly faster, not much faster, but it would have gone, it's not, you know, it would have also been compound interest, but it would have gone up ever so slightly faster. Now, that is where we were at the end of grade 11. Okay? So that is where we were at the end of grade 11. But I want to consider what happens, what is common to all of these situations which we have in this example over here. And what is common to all of these situations over here is that I only make a single payment or withdrawal or borrowing or whatever the case is. So if this was a case of investment, okay, I only make a single investment, okay? So this is wonderful if you hit a windfall, you win the lottery, you get a birthday present, something along those lines, that you invest once, okay? So in all of these cases, all that is happening here is I'm investing once, okay, or repaying once. However, that does not model the real world. And what I said to you last time is that the finance chapter is probably the topic in mathematics that most closely models the real world situation. So what I'd like to look at now is what would happen if I made lots of little payments, okay? So let's just zoom in and have a quick look at the graph, and let's just think what would happen here, okay? So instead of making a single payment and this single payment growing, okay, this idea of a single payment growing, Okay, so there's my payment. Okay, so there's my p-value, and it grows. Okay, what I want you to consider is a situation where maybe I have let's make it a smaller payment. Let's just call it some x value. Okay, so make this x value. It grows in a month. It then shoots up because I make another payment. It grows a bit more. It shoots up because I make another payment. And every single time I'm paying in a x value. Okay, and this thing shoots up, and now I pay in an x value, and it grows another month, and it shoots up another x value because I'm making these repeated payments. And so I'm making, in this case, the difference between a single payment versus a regular payment. And each of these growths in between the payments is exponential. But you can hopefully see that these vertical climbs, because I paid in an amount of x, must lead to faster growth than the single payment. Okay? Now, obviously, if that single payment was a really significantly big payment and the period of time was fairly short, then the blue graph would be perhaps more advantageous. But in most real life situations, this regular payment scheme, okay, leads to a much better result over time. And this red payment scheme has got a fairly interesting name. It is called an annuity. Okay, it is called an annuity. And where it comes from is the idea that were I to make an investment over time. So let's have a look at this as a timeline. Okay. Okay, sorry, let's just put that a little bit neater than that. Okay, were this to be an investment over time. Okay, and let's say we made this over 10 years and we're doing it as an and, so let's just consider what happens. Okay, so let's do 5 payments of 2,000 Rand each at 6% per annum. Just something really straightforward. Okay, it is compounded annually. Okay, I just want to keep this thing fairly straightforward for the moment. Okay, so he puts in a amount of 2,000 Rand. Okay, and this 2,000 Rand will get 5 years worth of interest. So this here would be 2,000 Rand 1 plus 6% to the power of 5. However, after a year, so that would be at year 0, the initial payment. After a year, okay, I put in another 2,000 Rand. That's going to now lie here. Okay, 1 plus 6%. But I hope you can see this is not only going to be worth lying here for 4 years. The next payment will lie here for 3 years. The next payment would, for example, lie here for 2 years. Okay. And the final payment, because there's no real point in making a payment and withdrawing it, so the final payment at the end of 4 years would only lie here for a single year. So my total savings, okay, is going to equal 2,000 1 plus 6% to the power of 5 plus 2,000 1 plus 6% to the power of 4. And I'm going to repeat this calculation for all of these. 1 plus 6% to the power of 3 plus 2,000 1 plus 6% to the power of 2 plus 2,000 1 plus 6% to the power of 1. Now, what I'm hoping you can see is that because we are adding every single time, okay, we're adding different things every single time, this might be linked to the idea of a series. Okay, and again, if I was to look at this as a series, my next question is it arithmetic or geometric? And hopefully you can see that each term, okay, each term is actually simply a multiplication of, because of the powers, it is simply got an R value of 1 plus 6% would be my R value. Okay, now this would be geometric with an R value of 1 plus 6%. So again, we can take this idea for this particular sum and we could say, hold on, this would equal, well, let's have a look at it. We've got R equals 1 plus 6%. We've got the first one, okay, the very first one, so A, sorry, wrong letter A equals 2001 plus 6%. Okay, that's our first term. And that's N, in this case there are 5 terms, so N equals 5. Okay, so we've got a formula for geometric series that says to us, hold it, just trying to get it here quickly, that A equals what am I doing? So that's, sorry, wrong formula. That sum of n equals a r to the n minus 1 over r minus 1. So if I was to plug these values in here, I would get a formula that says, cool, my total savings would equal 2001 plus 6% to the brackets of 1 plus 6% to the power of 5 minus 1 all over 1 plus 6% minus 1. Now, we are very close to actually having our formula. And I'm not going to go through it too deeply because it's not actually examinable, but it does come from this idea of finding a compound, the geometric series. And so what we have here is a formula for the total savings. And this thing is what we're going to call the future value. Okay? We're talking here about the future value. Okay? So FV stands for future value, and that will become quite important that we understand what the F and the V stands for. Okay? Future value is our formula. Okay? Now, it's on the formula sheet, and I'm not going to go, as I said, it comes from an expansion of this idea of the geometric series, but you will see on your formula sheet that says FV equals X 1 plus I to the power of N minus 1 all over I. Now again, if you just go back to what you had on the previous page, it would actually be over the power of 1 plus I minus 1, if you compare it to the formula, S of n equals a r to the n minus 1 over r minus 1. If you compare the black and the yellow, you'll see that you can see the history of the formula. You can also see how come that 1 plus I minus 1 falls away to just become a formula of just I. Okay, so there's only an I in the denominator. Okay, now admittedly, this is for a payment that is made a little bit later, and we'll talk about that now when it comes to examples. But X is my monthly repayment, okay, or my monthly investment. Okay, I is my interest rate, okay, per cycle. Okay, and N is my number of cycles. So again, we have a formula where it has 4 variables, and it's the exact same in this regard with the grade 11 syllabus, that actually all we're going to do is identify 3 values in the text, plug it into the correct formula, which hopefully will be the future value formula. We do need to be careful. There is another formula that we'll encounter in the third episode called the present value formula. But as long as we can identify that we are looking for the future value, we plug into the formula and use a calculator to work it out. Now, we will see that there is a bit of difference in one or two examples, but again, here is our formula. Let's have a look. So again, since we don't know the formula, let's just write it down for us. FV equals x 1 plus I to the power of n minus 1. Generally speaking, we use square brackets just to help us with remembering where things go, over I. So let's have a look at this text. Businesswoman deposits 9,000 Rand to account. She continues to make monthly deposits of 9,000 at the end of each month. So if she's making these deposits each month, this would be our X value. Not sure why it's not writing on. Okay, so we therefore know that 7.2.1 X would equal 9,000 Rand. Okay. She continues to make things at the end of each month until the end of December 2018. So now again, we just got to be careful with our number line. Okay. So if we are talking about her making this payment, okay, so let's just go 2014 to 2018. We need to be sure that we understand that the first payment is made at the end of January. Okay, so this is at the end of January. And this last payment is made at the end of December. Okay, so therefore, there is no payment made immediately. Okay, her first payment is only made 1 month into the cycle. Okay, as a result, she makes 12 payments in January in 2014, 12 in 2015, 12 in 2016, 12 in 2017, and 12 in 2018. As a result, hopefully we can realize that therefore n equals 60. Okay, and we can see here again from the text, okay, that the interest rate is 7.5% compounded monthly, so we can write that down. I equals 7.5% compounded monthly. So again, we're talking here in months. Our cycles is months. Our interest rate is in months. We are happy with that. So we have checked, okay, that this was in months and this was in months. Okay, so now we can just plug into our formula. Okay, calculate how much money was in the account after these things have been done. So again, it's not quite as clear, but you can see that they're talking about immediately after all of this. So because they're talking about immediately after, okay, we can assume therefore that, sorry, it's bugging me just a little bit quickly. I do want this to be going to the back, but it's not. Yes, there. Go to the back. Okay, because they're talking here about immediately afterwards, okay, we can see that they are talking about, therefore, a future value. Okay, because they're talking about here after the amount, we must be talking about a future value formula. Okay, so this is telling me that I want to use the future value formula. So I'm going to plug it, as I said before, the key thing is this line over here. The future value will be 9,000 Rand, 1 plus 7.5% over 12 to the power of 60 minus 1 all over 7.5%. Please don't forget that this is over 12. And so again, one of the key things here is that this 12 is still part of the interest rate. Okay, so again, let's have a look at what's going to happen. Okay, I now need to type this thing in, and the skill now is knowing how my calculator works. So it's 9,000 Rand, brackets, 1 plus 7.5%. And again, I wish we had the drive on this thing to be able to see the screen, divided by 12, close brackets to the power of 60, minus 1, close the brackets, all over 7.5%. Again, I'm using the percent symbol on the calculator, divided by 12, chug, 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 let the calculator do the work. And I now see that it says to me that, believe it or not, even though I only saved 9,000 Rand per month, the fact is that I now have 652,000 743 Rand and 95 cents. Okay, so this was quite a good interest rate at 7.5% compounded monthly, but for putting 9,000 Rand away every month for 5 years, I've actually increased my money up to 652,000 Rand in this 5-year period. Okay. Cool. 7.2.2, again, they want to go ahead. Okay. And so what's going to happen now is this lies for a further n months in the account. Okay. The interest rate remained unchanged and no further payments were made. So again, please understand that because of this statement here, that no further payments were made. Okay. We must now not be dealing with the F formula, but we must now be dealing with the with the AP formula. So 7.2.2, the correct formula would be A equals P 1 plus I to the power of N, because we're now talking about this money lying here with no further repayments. Okay, again, we said we want to use the choose the correct formula. This is the correct formula to use for this question. Okay, we are not using the future value formula. So we need to identify in the text. We now know that P equals 652,743.95. We are leaving it there for n months, which we need to find n. So n is the thing we are looking for. I is given to us as being unchanged. So that was 7.5% per annum compounded monthly. And we wanted the interest to grow. Okay, so we want the interest to grow to 190,214.14, which implies that therefore the A value would be, we got to add that onto the marks. It's the interest, it's the extra, 214.14. The total amount now would be 842,958.009, and we go and plug this into our formula. Okay, so please remember that there is a formula which the accountants will know, that A equals P plus I. Okay, and here we're using the capital I on purpose. Okay, so we're going to plug this in, and 842,958.09 equals 652,743.95. 1 plus 7.5%. Sorry, this pen's starting to irritate me just a little bit, so let me just get a little bit neater than that. 1 plus 7.5% over 12 to the power of n. We're going to do what we did previously. We're going to divide by this, answer divided by 652,743.95. Okay, so we've got that value. So we've got the log of 1 plus 7.5%. Again, trust your calculator to do it properly. Divided by 12, okay, of this value, of this answer. And we get an answer of another 41 months. Okay, so the log of 1 plus 7.5% over 12 of 842,958.09 all over 652, again 652,743.95 equals n, which now equals 41.044, so 41 months. Okay, and we're done with that question. Okay, I don't really want to do too much here. I just want to go again. I'm not going to do the calculation necessarily. I just want to again look at it. It's worth 3 marks. So they don't think this is massively difficult. Okay, again, the key thing is to know which formula, okay, and what the variables are. So let's go through this one very quickly. Okay, I'm not going to actually do the calculation. I'm just going to set up the formula. 30 June 2013. So we're looking at a timeline. Okay, so this would be the end of June 2013. Okay, and at the end of every month thereafter, okay, he put 2,500 into his account. Okay, that pays 6% per annum. Okay, compounded monthly. Okay, he wants to continue this until the end of May, okay, 2018. Now, we've got to be careful here, because from the end of June to the end of May actually is a full calendar year of payments. It's actually a full set of 12 payments. Okay, so we need to be careful here. We might want to actually count on our hands. Okay, but it is important to get the end value correct. So we can see that from here the X value is 2,500. Okay, we can see the interest rate is 6% per annum compounded monthly. Okay, but only by looking at this timeline. Okay, and I have a habit with my timelines to always put the amounts on the top line and to always put the interest rates on the bottom line. Okay, so until the end of 2014, 15, 16, 17, 18, okay, that's a 7, okay, each of these is 12 payments, okay, so therefore we should be able to see that again for this example is 60. Having got our three variables, we plug and play. Future value equals 2,500 square brackets, round brackets, 1 plus 6% over 12 to the power of 60 minus 1 all over 6% over 12. Okay, again, as I said to you earlier, this is worth 2 of the 3 marks. This final method for knowing how to use a calculator is only worth 1 out of the 3 marks. Okay, so again, we do have a brief moment, so let's have a quick look. Let's type it in. 2,500 square brackets, round brackets, 1 plus 6%, sorry, 1 plus 6% divided by 12, close the brackets, raise it to the power of 60, minus the 1, close the brackets. In my denominator, 6% divided by 12 equals, and it tells me that I will have a future value of 174,000, sorry, wrong color, a future value of 174,425.076. So 076 would be what? We'd need to round off to 2 decimal places because it's money. So we're going to come back here with the eraser and realize that 076 would round off to 0.8. And there we are done with the lesson on future value. Thanks for your time. Good luck.